disadvantage already. Summer's going to cut out all of that kind of stuff that you may have built up, and depending on how well you processed OChem 1, if it was more, I'm just trying to cram as much information in as possible, all of that is gone. And so you have to effectively rebuild from the ground up. Okay. Since we don't have any immediate questions, where I figured we would kind of start, and I immediately went for a whiteboard, and I don't know that I want that, would be these questions. I have not graded all of them yet, and by grade, all I'm going through and doing is entering full credit and then trying to provide some comments about what I saw within your quiz. So yeah, I think it's important to go back through and look at some of these, particularly because there's some high value behind the intent of these questions. So first and foremost, I would argue probably one of the simplest ones, okay, draw a representation of a p orbital, was missed by a significant portion of the class. Okay? And that's probably because it's one of those real early on in the semester things, so I don't need to worry about it. We kind of memorize it real quickly and then just leave it be. In second semester, we do lots more stuff with molecular orbitals. We kind of already talked about that in lab, with the Diels-Alder reaction. The Diels-Alder reaction runs by looking at molecular orbitals and how those things function. So we will constantly keep going back to molecular orbitals to try and explain how things are functioning and where things are at. So we need to be familiar with them. When we're talking about an s orbital, we just have a sphere, and a p orbital is the dumbbell shape. Okay? Relative to the nucleus, okay? So where's the nucleus in the s orbital? Okay, there, that's better. Okay, in the middle. That might make sense for a sphere. That's a little bit clearer, a little bit easier to understand. Where's the nucleus with a p orbital? Okay, it's the node in between, okay, which introduces a new concept, okay, or a new term that you're probably going to encounter in one of the smart work homework. So when it talks about molecular orbital theory, is it's asking to count nodes within things. Nodes are effectively a 0 point within the orbital. So p orbitals have a node. Okay? That node is noticed as a kind of 0 point. Okay? Why do we not see that 0 point in the s orbital? Because technically there is one, not in the 1s, but in the 2s, in between the spheres, we have nodes. We can't see those very well, so we tend to ignore them. So when we're talking about our nodes, we're talking about kind of the xy planes, the other axis too. Okay? What's happening at a node? Okay. What do the orbitals describe?
Where the electrons are.
Okay. It describes effectively where the electrons are, the motion of the electrons. Okay. Well, do electrons behave as particles or do they behave as waves? Okay. You get a little bit of a mix of both. There's the particle-wave duality, but the wave is a large aspect behind it. The more we know about the about an electron, its location, it behaves more like a particle. The less we know, the more it becomes like a wave. Okay? So when we're talking about a wave, I'm not even going to attempt to draw like ocean waves. Okay? We've got sine, cosine, whatever you want to look at. We've got waves. And we look at that wave, we can reference a couple points. Okay? We could reference this point, and we could reference this point. What is the difference about that red versus the purple point?
Different energies.
They're all on the same wave. They have the same energy, they have the same push-pull features, so the energy really isn't any different. Okay. We've gone to the beach, right? Let's pretend this is our wave. We'll erase that part of the wave so it's not really visible there. Okay. And we've got a little person right here. Here's a little kid chilling out at the beach. Which part do we care about hitting the kid? The red. because it has a positive value. The purple has a negative value. It's not an energy, it's the amplitude of the wave at that given kind of instant. Right? So we have positives and we have negatives. But to transition from positive to negative, what do we have to transition through? A 0 point. What is the 0 point? The node. And when we look at an s orbital, we can't see the node. So it's still representing the motion of an electron as a wave, positive or negative, but at any given instant, when we look at the s orbital, it is either all positive or it is all negative. We don't get a choice. The p orbital is different. The p orbital is different because it has a node built into its wave expression, which means at some point it is positive, and in the exact same orbital, at the other point, we have a negative amplitude. How do we see this visually? That's the shading features. Okay? And this positive and negative becomes important because when we talk about making molecules, we're talking about overlapping orbitals. Right? And for there to be an orbital or a bonding interaction, we need the amplitude to increase. We want to see more electron density in that space. We don't want to see less. So if I, for instance, now let's make this atom A and atom B in the case of the s orbitals, and I bring them close to each other, if atom B is manifesting as the the negative amplitude, and atom A is manifesting as the positive amplitude, what happens when those two orbitals interact? Okay. Progressively bring them closer and closer until my two orbitals are overlapping each other. And if one is negative and one is positive, what happens at that intersection? Elaborate shaking your head, because shaking your head isn't a horrible answer, but it could also mean like, oh my God, what am I looking at?
Is it, there's nothing? Just
Yeah.
cancel out, so there's nothing.
Okay? They cancel out. If you take the positive amplitude and the negative amplitude of two things and you add them to each other, they cancel out. They become 0. Which means what happens to the likelihood that we find the electrons between those two atoms? It's 0. Do we get a strong bonding interaction? No. Okay? So when we're talking about making bonds, we need to see our orbitals overlap in the same phase, which means we have to be aware of these phase aspects when we're talking about our orbitals, particularly for our p orbitals. The s orbitals, depending on what we're trying to do, and if we're looking at molecular orbitals and all sorts of other fun stuff like that, we can start talking about bonding and anti-bonding orbitals, which isn't a huge issue for us this semester. We're really going to focus in on the p orbitals, and we can talk about bonding and anti-bonding with those. S orbitals, meh. Kinda sorta? So what happens with the p orbitals? So let's get rid of the s orbitals. I think I heard someone say that when we talk about our p orbitals, I'm pretty sure I didn't hear someone say it actually, I think I'm making it up, that we have 3 p orbitals, right? We have one aligned on the y-axis, one aligned on the x, and one aligned on the z, right? So for atom A has all 3 of these potential options, and the Z1 is awful to draw, so never make me do anything on the Z-axis. If I bring in atom B, and it's now also going to interact, okay, I'm going to have these same potential systems come into play. Okay? And now what we want to think about is what's potentially interacting as we bring these together. So what orbitals would you bring together to create an interaction? Which interaction, as we've drawn them, would be the most stable interaction? Okay. Y with what? So you're saying PY, there, okay, I'm going to look at the PY of A, and what do I want to interact it with? Okay, so you want to look at this interaction. And you want to call that the most stable interaction. In face. Elaborate your face. That sounded really weird.
I mean, I feel like they all would so P A of X would also match the B and same with the Z, the other Z.
Okay. So I'm cool with that. We're not going to do any weird cross interactions. We're not going to take Y and interact it with X. Okay, why not?
Not on the same axis.
They're not, well, why does that matter? Can't bond. Why can't they bond? What did you say?
They can even interact because they're in different.
I love it. I want to hear. There's a word I want to hear that we just talked about when we bring our orbitals together. What has to happen?
Overlap.
They have to overlap. And if we start taking the PY and our PX, they aren't going to overlap well. At best, the PX overlaps in the node of the PY. Well, there's nothing in the node of the PY, which means I don't get an overlap. So it doesn't make sense to cross the streams, if you will. Okay? Right. So now between those sets, which one's going to generate the strongest interaction? Said PY, why PY? So let's try it this way. How is PY different from PZ? All right, here's Y. PZ. Are they any different? No. So if you're going to tell me PY is the strongest interaction, you also better be telling me PZ is equally as strong. Okay? Yeah?
Yeah.
Okay, cool. Is it the strongest interaction? What happens with the PX? And what's going to happen in the case of the PX if we align phases a little more appropriately? PX start to overlap. Okay? Where was the PY? The PY was in dead center of the PX. Another PY. Here's another PY. Which interaction do you think is stronger? The PX or the PY? Why the X? They directly overlap. Okay? So if we're looking at just the absolute, I'm taking atomic orbitals and I'm going to overlap atomic orbitals, we would say the PX is going to generate the strongest interaction because they directly overlap, whereas the PY and the PZ don't. Because they directly overlap, they could generate a bond type, okay? A different bond interaction than the PY and the PZ. So I want to name that. What do I name that? Try it this way. How many bonds do you see clearly based off of overlap? You see one. Right? So if we were going to label that, we might call that what kind of a bond? Okay? Sigma is the one I was fishing for. I was trying to hint you into single. Okay? But yeah, a sigma bond. Okay? Direct overlap. Okay? The PY. Should the PY ever overlap then? Do they ever have the chance to share electrons if the orbitals never overlap? No. Except we get this nasty, well, doesn't it overlap if you look at the other axis, though? Well, yeah, but there's this giant space in between where the electron's not allowed, right? So electrons can't just jump through nothingness, because that's not how things work. That's how electrons work. Electrons do this thing called quantum tunneling, and they can tunnel through space. Okay? They can only tunnel short distances, which means if I take these p orbitals and I move them out here, they can't tunnel and I don't get that overlap. I only get it when they happen to be brought just close enough, thank you sigma bond, that now they can tunnel through that space and I get a long distance, if you will, overlap. That long distance overlap is a different type of interaction. We would call that an indirect overlap, and we could reference that as what kind of a bond? A pi bond. Note, not a double bond, because a double bond is the conjunction of both a pi and a sigma bond. That's why it's two bonds. That's why we call it a double bond. just the overlap of the p orbitals would be a pi bond, okay, or the indirect overlap. Kind of make sense? So this is the lovely atomic world. Okay? When we go through to make our reactions, are we looking at atomic interactions? It's a hard question. So if I wanted to explain the bonding patterns that I see in CH4, I would say I could take the 1s orbital of all of my hydrogens, right? Because that's all they got, that 1s orbital. And I would overlap it with what atomic orbital of the carbon atom? Okay, and to help you out, carbon's electron configuration, 1s2, 2s2, 2p2. What atomic orbital is being used to overlap with the hydrogen 1s orbital? P orbital. Awesome. Love it. Let's work with it. Okay. If I take a look at the p orbitals, what is the angle between all of my p orbitals? If I compare py to px, what's the angle between those? 90. What is the angle between my carbon, hydrogen, carbon? There's a couple good answers that you could drop into that one. Should I give you the less good answer? 109, there's the best answer. And technically 109.5, I think. That's the best answer behind that. Okay, so not 90. That was the less good answer, but equally valid. Okay, why is that important to us? If I'm going to explain the bonding patterns here, and bonds are where my electrons exist, I had better have orbitals to explain where they exist. My atomic orbitals don't explain it. They don't work. So what did we come up with as a half-assed answer? What orbital does carbon use to make that bonding interaction? Say again.
Between s orbitals.
We would go back up to the atomic orbitals and say, I need 4 equal orbitals, okay? Of all of the orbitals I got, I'm probably not going to look at the 1s, because that's an internal shell. I want to look at the outside. Okay, I'm going to look at the external shell, the valence electrons. Okay, I've got 4 orbitals there. I have the 2s and then the 3 2p's. Okay, that would give me 4 interactions, but the bond angles don't align, so I'm just going to say, F it, they're all probabilities anyway. Let's mash it all together into a giant pot and pull out whatever orbitals I want to make out of it, out of those probabilities. And I'm going to call those hybrid orbitals. Okay. Since I didn't have to use all of the p orbitals necessarily, I want to be able to name this new orbital. I could name it Sally. Right? Perfectly acceptable. That's a little bit of a weird name. It doesn't have any kind of secondary meanings associated with it. We would just have to memorize that Sally means that we used S and 3Ps. Right? What did we decide instead as scientists? What do we call the hybrid orbital that involves 1s and 3p orbitals? sp3, because there were 3 p orbitals. That's the name of it. Right? So when we're talking about our molecular orbital theory, we had hybridization initially to explain these things. That generates those orbitals. Okay? What we will find for the most part this semester is that we're going to focus on sp2 hybrid or even sp hybrid, because what that leaves over is unhybridized p orbitals. Those unhybridized p orbitals give us some interesting and different chemistry. Right? But I have to understand how those p orbitals potentially interact and can change in their local environments. Right? So we need to know what a p orbital looks like. We need to know that it has phases. It has this positive and negative amplitude associated with it. Right? We then go through and try and make a bond using p orbitals. Okay? So if we make the bond with p orbitals, remember where our nucleus is, it's the dot there. So in the subsequent question, where are the electrons in the bonding interaction between atom A and atom B? They're above and below. There are no p orbital electrons in the middle, because what's in the middle of our p orbitals? The node. I can't put electrons there. Okay? What else is actually in the middle? Why is there a node there? Because there are technically electrons there. They just aren't p electrons there. There are sigma bond, which could come from any of our s-type orbitals. That's the electrons running through the middle. Our pi electrons are running above and below. Why does this become important and relevant to us? Well, if we're going to talk about reactivity of this potential molecule or any of our molecules, we need to be aware of what those p electrons could do. Okay? So we could move to the next question. The next question said, most stable cation, and the two cations I gave you this one. Whoops. And I think I gave you this one. I said, which one's most stable? What did the majority of you tell me? Told me this one. People then mixed results actually explained and said that that is tertiary versus primary, and tertiary is more stable than primary. For the record, lovely. Wrong, but lovely. Okay? You're addressing the difference between tertiary and primary. Is the bottom one primary? No. It's got resonance. How do we know it has resonance? Well, where's a positive charge? What orbital holds a positive charge? A p orbital, which is really important for us, because if we redraw that molecule, okay, in a straight line here, we'll talk about our sigmas moving through. There's our cation, the positive charge, but then I had a double bond. How do I make a double bond? To make a double bond, I need a pi bond. That's looking at p orbitals. So that double bond has these p orbitals sitting out over here. And there's electrons jumping around in those spaces. And if I have that carbocation that is a p orbital, what could those electrons do? They could tunnel also all the way out there. And if we're now talking about stability, what happened to that positive charge? It's been neutralized, sort of. Because if that middle electron jumped over, what happens to that middle space? That one would become our positive charge. And there's some big air quotes on that because we have to follow how we talk about our electrons moving. So that means in the case of these comparisons between these two structures, this is the more stable one because it has resonance stabilization. Tertiary was more stable than primary just because there were more electrons nearby. We didn't talk about the electrons moving, they're just near. Right? We could use this as you could be wealthier if you were near a bunch of rich people. Probably because maybe they just throw money around and you happen to grab some. But if you're friends with a bunch of rich people, they may give you the money. It's not just falling off of them and you're picking it off of the ground around them. They're actually giving it to you. Okay? So we're looking at how the electrons have the ability to move and different levels of that stability. If we think back to what we talked about Tuesday, we referenced the Cario, that was charge, size, electronegativity, resonance, induction. Okay, let's just stick with those for the moment. If we talk about the difference between tertiary and primary, is that charge? No, it's the exact same charge. Is that size? Is the atom that's holding the charge different? No. Is it electronegativity? No. Is it resonance? No. Is it induction? No. Well, then why are we saying tertiary is more stable than primary? Because after you hit those major categories, there's another category that's the catch-all of, like, there's a bunch of other stuff that could contribute to stability. And one of those things happens to be the substitution pattern. And if we reflex into just memorizing, we start overplacing the substitution pattern higher than the other 5. So make sure you reference those other 5 positions first before you start ranking your stabilities. Kind of, sort of? Okay. So if we understood our p orbitals, we could explain what's happening within 3. We have the legit ability to move electrons that we don't have in the other one. We can use our memorization of those terms and that ranking system if we didn't want to use that understanding. The next 2 are radical things. We'll come back to that. If we talked about most reactive atoms, never mind. I don't want to talk about most reactive atoms. We'll go back to the radicals. If we're talking about the radicals, okay, this is a dangerous one because I don't think I personally don't like talking about radicals very much. But if we look at alkanes, just a standard alkane, okay, why are they only susceptible to homolytic bond cleavage? Okay, that word homolytic probably only showed up in the radical video, okay, that you were supposed to have watched that you likely did not because I said, probably a couple questions and you could probably skip it and just accept that as a loss. Did you guys talk about radicals? Yeah, probably talked about it a lot real early on in the semester. Okay, no excuse. What's homolytic mean? It's okay.
Been a while.
Homolytic versus heterolytic. Almost everything we do is heterolytic. Okay, so if we look at an individual bond and the electrons between those 2 atoms, heterolytic means the electrons go to one atom. Homolytic means the electrons go split back to each of the atoms. Right? So AB, that red arrow is heterolytic. Homolytic would be the blue one. In the case of that blue one, what do we end up forming? Radicals. In the case of the red one, we end up forming ions. Positives and negatives. We get ions that come out of those. Okay, it doesn't have to be hard. Right? So why, when I look at an alkane, would I really only expect homolytic bond cleavage and not hetero?
Really nothing going on. It's just
Elaborate. Yes, there's nothing going on. I understand what you're saying with that. So if we're saying hetero, right, what's the something that's going on in hetero that makes you say it can do hetero?
bonds are breaking.
Bonds also breaking in homo. I don't accept. There's a difference in electronegativity between atom A and atom B. That difference in electronegativity is what's really forcing the heterolytic cleavage. And if I look at an alkane, we're looking at carbon to carbon and carbon to hydrogens. Those, by definition, are nonpolar covalent bonds. Because they are nonpolar, the difference in electronegativity is negligible. There is no difference, effectively, which means I can't do hetero. The only thing left for me is homo. Right? That's what we're trying to address. So when we think through the radical stuff, which in theory you're now going through and watching, and I would probably equally say, even now in this semester, where it's now part of the content, you could probably skip the vast majority of it. Right? But what it's looking at is how do we get alkanes to react? Because they don't. We get them to react by doing something radical. That's the whole radical process. Right? And if we push on that, that's where we go through and get different different reagents to force homolytic bond cleavage. Okay? And there are things that stand out to help with that. Those things show up in question 6, I think. Nope, it was a different question that I didn't give you. Right? Those things would be stuff that we would add to our reagents to help us know, ooh, that's going to do a homolytic cleavage radicals versus that's going to do a heterolytic cleavage ions. If we now push to the mechanistic steps when we go through a radical reaction, radical reactions don't follow the nice, simple, elementary mechanistic steps that we've talked about, or that we learned about in OChem 1, or that you're reviewing at the beginning of this semester. Because all of those are based off of heterolytic bond cleavage. Okay? They're all going to generate some form of ions. Radicals go through a different system. We have an initiation process where we have to form the radical. How stable are radicals? They're not. This is why when we walk around outside, we put on sunscreen, because we're afraid the sun, the UV light from the sun, is going to do what? Create free radicals. Free radicals are bad. Uncontrolled free radicals are bad. Right? We process, all of our energy goes through radical states. It's just in a very niche corner that makes sure it functions the way it's supposed to. Okay? Sunlight's going to go through and cause free radicals to happen everywhere. That's a problem. Okay? That's how we get cancer. Okay? So we've got an initiation system. Okay? How likely is the initiation system? Okay? So in this question, what's the most likely thing? The final radical substitution product. Damn, that was not the question I thought I asked either. Right. What's going to form? Actually, no, it is. The final radical substitution product. Is the initiation the most likely thing to happen? Right. And we've got an answer for this. When we step outside into the sun, do we have instant cancer? No. Right? So the initiation happens at very small levels. Right? We still put on protection because of the amount of sun exposure we get. There's a large concentration, even if it's a small percentage, a large concentration could be dangerous. Right? So the initiation is not likely just because that's not going to be a final product, but it's also not a likely thing to happen just in general. Okay? Propagation. Once I have the radical, it now reacts. And how it reacts, what's the most likely thing it's going to encounter? More radicals or neutral things? Neutral things. The radicals were very unlikely to form from the get-go, which means the odds of two radicals combining and hitting each other and finding anywhere within the system, highly unlikely. Right? So that radical is now moving around, hits a neutral thing. As it hits the neutral thing, it will necessarily produce another radical because it's bringing in one electron. We have to balance it out. It has to kick out another one electron. So that's our propagation. Right? Propagation, it now continues because I have another radical that can continue to react, continue to react, continue to react. Does that make sense for our final product? And what I was fishing for there was pretty much exactly that, the 50-50 response. About half the class said yes, the other half said no. Let's look at the termination. What happens in the termination?
No more radical?
Two radicals find each other and cancel out. Right? What's the concentration of our radicals? Very, very, very small. Right? So while termination can happen, is it going to happen a lot? No, which means if I'm talking about which of these mechanistic steps is most likely to form my product, it ain't the initiation because I don't produce a lot of radicals. And it's not the termination, even though it sounds like the end, because the termination requires two radicals to come in contact. And there isn't a lot of radicals floating through the solution, which means very counterintuitively, our final product happens in a propagation step, not in the initiation or terminations. And if we understand the radical reactions and how they work and how they're based off of, which is largely concentration, and that radicals are incredibly unstable to begin with, we can kind of piece together those processes. Okay? They are also non-linear mechanisms. I don't get to go from starting material to product in a nice clean line. It doesn't happen. Okay? We go to starting material to radicals. Those radicals can react with anything, okay, which could produce more radicals. It could also be a termination. Okay? It could be something entirely I don't want. It's all kind of concentration dependent. That's where those get dodgy. Okay? And if we move to the last thing, the most reactive part. Okay? Let's start with HBr. Okay? We'll just go with it. What's the most reactive part in HBr? So pause. Can you name HBr? You're like, well, we didn't name inorganic compounds in OChem. That's right, you named them in Gen Chem. You should have learned it in Gen Chem. How do you name HBr? Okay. Admittedly, potentially a challenge. Let's make it slightly easier. It's going to get the same result. Hydrochloric acid. Okay? If that's hydrochloric acid, and I now make this HBr, what is the name of that one going to be?
Hydrobromic.
Cool. Hydrobromic acid. How are acids reactive? What is the definition of an acid? Okay? And this becomes an important thing to know. We absolutely need to know the definition of what our reagents are. Otherwise, you must memorize everything. And if we know what the definitions are, we can apply those definitions on top. Acids donate protons, H+. Okay? So you could think through other H3O+. H+. Are those acids? Yeah? Why are they acids? And I have hydrogen. Our acids are H+. Which means if I'm now trying to figure out how this molecule reacts, how does it flip and react? The hydrogen. And how does it act? It acts as an acid. Done. Okay? I saw a couple suggestions, we'll draw it up on the HCl, which were neat. Drawing arrows. Cool. What do arrows mean? Movement of electrons. Fantastic. Okay, we would expect the electrons in that bond to move to the chlorine. Yes. All right, absolutely. What is that going to produce? They're both ions. Which one's the reactive ion? Ooh, and that could be challenging. Well, both are reactive, aren't they? Well, the way that I would describe it is use your real-world experience. Have you heard of salt before? Yeah? What is salt? Sodium chloride, right? And we've heard of acids before, HCl. Okay? The only difference between them is hydrogen, really. Okay? If I drink salt water, what's my response? Ugh. If I drink hydrochloric acid, what's my response? Dead. Okay. What was the difference in chemistry between those? Oh, I have a hydrogen in one. What does that mean? Hydrogen's the reactive piece. That's the one that's doing the dangerous stuff for me to move around. Right? Don't drink anything. Oh, I mean, that's excessive. Don't drink anything within our labs. Right? But those kind of thoughts, use the content you already have. Start to draw those out. Perhaps, if the people that drew this arrow had drawn the products of that, they might have been able to reason through it. Instead, what they did is drew the arrow and then just circled that. By not having drawn the products, they're missing some of that critical information, and they've hyper-focused that chlorine took the electrons. Yeah, it did. Can chlorine stabilize the electrons? It's charged, yeah, that's bad. What's the next thing on my list? Size. Is chlorine big? Yeah, it's pretty big. What's the next thing on the list? Is chlorine electronegative? Yeah. So if we look at our list, the top two like high priority things scream chloride's okay. Okay. Can you make chloride react? Yes. How are you making it react? You're putting something more positive near it. You're changing the positive to react with it, not the chloride itself. Okay? It's a balance between both those pieces. Make sense? Cool. Let's move to the next hardest one. Our favorite answer was this. Circle the freaking atom. Okay? The thing that's reactive. Okay? BR2 is a tricky one. You want to know why it's tricky? Or how it's tricky? What do you see when you see BR2? Okay. They're the same. If they're the same, connected to each other, what might their reactivity be? Nothing. Okay, so you might go with nothing. What's another option? What else do you see when you look at BR2? True. There's a lot of electrons, right? There's a lot of lone pairs. So a lot of people will go through, oh, BR2, that must donate electrons because it's got lots of electrons. No, it can't donate electrons because if it tried to donate electrons, you would make the bromine positively charged, which it doesn't want to be. Okay? But if one of those bromines takes the electrons away, what would we produce? Well, we'd get one bromine with the negative, ooh, dangerous, versus the other bromine. What was that? With a positive. Which of those two things is reactive? Why is the positive more reactive? Ish, there's a better explanation. Would you say, Josie? That's the same kind of thing as the positive.
Negative is stable.
Yeah, you're still pushing on the negative. There's a big reason why the positive is more reactive than the negative.
It's octet. Is it?
There it is. When we talk about drawing out Lewis structures, this is going to show up on your final exam. Okay? They will ask you which of the following drawings is the best. Okay? And universally, students get it wrong because they jump on charges instead of octets. Octets are more important than charges. If you're missing an octet, that is screaming reactive. Right? Which means when we go through to identify this becomes real tricky. You should be circling one of the bromines. Doesn't really matter which one. And then theoretically, we should identify how it would react. Okay? If we're going to circle one of them, the one we're circling is going to be the positive one. And if it's positive, how is it going to react? What does it want to do to stabilize? So you could call it an electron acceptor. Phenomenal. What else could you call it? You could call it an electrophile. Acids technically are electron acceptors, but we differentiate acids and bases because acids and bases are just talking about hydrogens. Right? So we reference the transfer of hydrogens there. If we're reacting positives that aren't hydrogen, that's where we bring in the electrophile nucleophile definition. You could go real fancy, which I don't like doing, but we'll add it anyway, mainly for Alex's sake. Lewis acids, you could call it a Lewis acid as well. I don't like the Lewis acid definition because it's too broad. It doesn't narrow the field of chemistry for me. It makes it really broad and more confusing than it already is. Right? Kind of, sort of? Cool. Should we move to the last one? Let's just erase all those. I think I had something like that. Okay. Some people just left it alone. A couple people ventured guesses, and they did something like this. Super happy with that. We could do better, but I'm super happy with that. Why am I super happy with that? What we've circled is the pi bond. The pi bond, as we addressed already through questions 1, 2, and 3, is a higher energy bond, therefore making it more reactive and more likely to cause reactions. Awesome. Why am I unhappy with this answer?
One of those more reactive than the other.
Those two pi bonds have different chemistries. One is internal and one is external. That changes their reactivity. Right? That was way more nuanced of a thing than I actually wanted to get into with that question, but I at least was hoping to see some differentiation there, right? An attempt to fight through it. Most of that deciding which one reacts faster has to do with the mechanism under which it's reacting, right? And if we're talking about our standard acid additions or our electrophile additions, more acid additions, right, we end up forming carbocations. The carbocation is going to be more stable internally than it will be externally, so the internal double bond tends to react a little bit faster because the intermediate produced is a lower energy. Okay? Kind of, sort of?
So the internal one would that be the one on the right?
Yeah, internal is the one on the right. External or terminal is the better word because it's at the end of a chain. Okay? Kind of get it? Okay. This, I would kind of hope, will be the last time we actually go through a quiz, but I figured this week we're probably limited in the amount of time we spent looking at practice questions or videos, and so I figured going through some of the details on these might make sense. Kind of good?
Why is the internal one reactive?
It depends on the mechanism that you're reacting. Okay? Under most of our mechanisms with our pi bonds, we end up forming carbocations. Where would you rather have a carbocation? More substituted. Okay? So our internal tend to react a little bit faster because of the intermediate produced in that chemical reaction. Where's my mouse? There it is. Well, I thought it was actually going to load. One of the other things that I find valuable, particularly if you don't have questions, so we're really sitting on this, yeah, I don't have any questions, Mike, we're just going to let you run.
Is smart working? This is showing a white screen. It was working earlier, but now it's just.
I was having those issues yesterday. I just had to like close that tab, refresh.
Oh, I did that whole
And
time.
yeah, I don't know. I had to do that.
It might even be reset your browser cache.
I was doing it earlier when I first got here and it wasn't working for me either. It just brought up a white screen.
Oh.
So.
And apparently I just broke the screen too. Yeah, it actually appears to not be loading for me either.
Because I tried to do the trial access and it let me accept it, and then when it asked if I wanted to keep using that one, I clicked on it and then it was just
Yeah,
so it's down to a second.
smart work is down.
Do you know when it comes back out or like that?
Whenever they fix it. I'm sorry, that's all I got.
Has it happened before?
Yeah. Sometimes it is just a browser cache. They may have run an update or something like that, and it has to reset. So it might make sense to actually delete your internet history, or not your history necessarily, but the cache, and try and sign back in and see if that works.
Okay.
Do you have a vague idea of what question you were looking for?
It was the first one, I think, on Diels-Alder.
Okay. I don't think I have any Diels-Alder here. Wait. if you're looking at the first one in Diels-Alder, so what I would push through is kind of looking at this kind of skeleton. And so in this process, okay, we want to address a couple things. Number one, pretend you don't have access to the lab because the lab is actually studying this. How does the reaction work? Okay. This is not a radical reaction, so we're looking at moving pairs of electrons. Where are the most reactive electrons in these structures? Pi bonds. Cool. Okay. Where should my first arrow start? Should it start from the red side or the blue side? Why? What?
More electrons.
Yeah. Okay. Really what we're saying is what's the nucleophile and what's the electrophile. Okay. And to a first approximation, the nucleophile should have more electrons than the electrophile. Okay. Since the structure on the left, our diene, has 2 double bonds, it has more electrons. So it might make sense to start that process. So we could go through and show an arrow where the electrons from the pi bond react. Okay. With all of these now bonds shown on here, we got our full set kind of saturated out here. What we would hopefully see is that that carbon has now exceeded its octet. Because it has exceeded its octet, we have to move the blue electrons. Where do we move the blue electrons? And if you haven't watched the video and you're only relying on the lab knowledge, it could get a bit dicey.
How close to the other pi bond?
These blue electrons will actually go to the other side. Okay? Which then means what happens to the next atom? Also exceeds the octet, so we move the purple bond up to here. So if we're moving through, here's where our purple electrons are, here's where our red electrons are, here's where our blue electrons are. Everybody see that? Okay. Next thing I want to add, we're going to add orange dots for the diene so that we see those. If we look at this product, so let's just evaluate, let's evaluate the starting material. Do we have any important considerations that you might want to think about when looking at the starting materials? You might be like, that's a tricky thing. I got to worry about that. I'm going to take that as a no. Let's look at the product. We look at the product and be like, that's a tricky thing. And what it may be boiling down to is we've not specified that these are carbons necessarily. These are open. Why does that become important? If I now add those labels, does that potentially help? I think it makes things a little bit muddier, which is why I didn't want to do it first, but it might help you see the next piece. What is special about the product? Hint. What is special about all 4 of those atoms? They are all chiral. Did we start with those atoms being chiral? No, we did not. Which means that chirality came into existence through the process of this reaction, running. Right? So to establish what should be wedged or dashed as we move around has to come from a very deep understanding of how this mechanism works. Right? And that's what we were talking about in the lab. Right? So what we've effectively got here is a C and a line that are coming in and interacting. Right? So we're now taking the paper, I guess this is the paper, right? And they're now somehow interacting. Well, what is changing? What is causing the new bonds to form? What made this new red bond? What electrons? From the pi bond. Where are the electrons in the pi bond? They're in the p orbitals. And where are the p orbitals? Above and below. So this viewpoint that we're looking at is already going to be insanely misleading, because we have the C and we have the line. Where are the p orbitals with respect to those shapes? They're coming in and out of the plane at you. They're on the z-axis. That's not easy to see. Which is one of the reasons why, if you watched my hands real carefully, as soon as I put up the C in the line, what did I immediately do? I immediately turned my hands down without actually explaining why I was doing it. Why would I turn my hands down? Now I can see the full alignment of the p orbitals, above and below. Right? We'll have to kind of pretend that's a p orbital there. That looks a bit misleading. Do it that way. Let's switch it that way around. Feel a little better about that. Okay? So there's our p orbital. Okay? There's also, I didn't like that pen anyway, a p orbital on that line, right? Okay? If they come together like this, do I form a bond? Okay? We might say, oh, I could form a pi bond, right? Except I can only form a pi bond after I've formed a sigma bond. And there's no s orbitals in that space right now. So how do I make the bond? I have to bring one under the other to make the connection. Okay? Or I bring this one above. And I conveniently locked the... Do you like that pen on it? Okay? And now I can make that connection. As I do that, that's going to force the stereochemistry for all four of those other spots. Okay? Let's see if I can pull that off a little bit. Can you stay there? Just stay bent. Right? So there's the thing. That's the sigma bond. That's the sigma bond to A. Oh, that's hurting my hand. That's the sigma bond to A. Okay? So when I go through and come over this direction, okay, and I make that sigma bond, those p orbitals are no longer up and down. What happens? They're going to rotate to become an sp3 hybrid. And as they do that, where does A end up? Where's A aimed? Where's A aimed? Is it aimed at you or away from you? Toward you. In this view, where is it aimed? It's aimed up. Okay? So it would be wedged. Okay? There's no way I have the finger. Oh, look at that. There's B, right? My pointer is B. As this comes over, there's A. Okay? Rotates to make this. Can you see it? Let's just go with that. Where's A? Or A was up, and then B is going to then be dashed going down. Okay? You might be like, dude, what kind of weird magic are you trying to pull with your hands? This is what you try to do with the model kits to help with that visualization. If you've got the model kits, you can help to see that. Okay? It's still incredibly difficult. And the major issue as we talked about in the lab, is that what we're trying to transition is a p orbital to an sp3 orbital. Model kits don't do that, okay? So you have to kind of pretend and think about what's happening as it occurs, okay? Oh, I gotta do it again. There are my fingers. Okay, there was the A, right? Okay. When we came in here, it was aimed up, right? What happens if I come in underneath?
Say behind now.
It's aimed down when I rotate that. Ooh, that's dangerous. You mean there's two potential products? Yeah, why? Why do I have to worry about two potential products? Ah, there it is. It goes all the way back to the initial question asked on the quiz on Monday. They're p orbitals, and p orbitals have electrons both above and below, which means we have to be thinking about how did those two pieces come together? Did they come together where they attached on top, or did they attach on bottom? Okay? So our initial viewpoint on those could change. Did I have a pen? Did I set it down?
Right there.
Yeah, of course I set it down. Okay, so we did that C. What do you guys want? A, up or down? Up, okay. So we'll make that A up, which then means B has to be dashed. What happens with C and D? What do you mean the same? One is wedged and one is dashed? Yeah. Well, which one's wedged, which one's dashed?
C will be dashed and D will be wedged.
Why?
Because A and D are the same size as each station.
There it is. How that reaction worked was simultaneous. Okay? Which means in our starting material, A and D are locked on the same side. Since I did everything at once, I can't rotate it so that D is now on the other side. So if I define A as wedged, D must also be wedged. C comes in there. Okay? Kind of, sort of? I would argue that's the easy part. The hard part comes in with the next one. No, because that was A and B, so there's my C, right? There's the C, there's that. So the bottom of my pen is what letter? Is the pen on top or on bottom of the C? On top. It would be I. Okay, everybody okay with that? The top of the pen would be J. So if I go through and look at this reaction, when I align this in and it makes that connection, where does this pen have to rotate? Can it rotate this way? Can I rotate this way? What happens if I rotate this way? What does it hit? The other molecule. What happens if it rotates that way? Oh, it doesn't hit it, which means when this comes in this way, what do we say that was? I must rotate where? Up. Which means in my drawing, I should be wedged. In my drawing, why did A go up? Right? There was my A. There was my C. Okay. When did A go up? Should A have gone up here? Does that look like A is going up? No. When does A go up? Ah, when it attacks from above. Real subtle, it went by real fast. Did you see the issue? What was the issue?
When it attacked on top and it rotated this way, and then when it came on the bottom, it was sent back.
rotated the other direction. So when we solved A, B, C, and D as far as their stereochemistry, we got those nailed down. What happened when we talked about I and J?
We switched it from attack to the bottom.
It's almost like someone was saying, I bet you're going to screw this up, and accidentally do a 50-50 swap on it and change the direction that it moved. Okay? You got to make sure that when you define one, that you maintain that same approach each time. Okay? For A to go up, we had to have the top attack. Okay? So there's our top attack. Where does the bottom of my pen, I, need to rotate? It has to rotate down, and J needs to rotate up. Kind of make sense? You've got so many moving, flipping pieces that you've got to make sure that you aren't accidentally swapping between both of those products. If we move to the other side, what's going to happen?
Do you mean F and E?
Yep, F and E. I think I swapped those, didn't I? We said A was coming in up.
Yeah.
Up, which meant, oh no, I went down. Yeah, I did that right. What happens with F and E? I, being on the inside, had to rotate away from the other structure, right? Where's E? The same relative spot on the inside, which means it's going to need to rotate.
Away.
Same deal, away. Right? This now becomes our glorious, awful picture of trying to memorize things. But this was only half of the things we could have memorized, because the other half, I'm not sure I'm actually going to be able to do it very well from memory, but we'll give it a shot. I think we just swapped them all. What have I produced? Oops. Sweet. I produced the enantiomer. Potentially. And potentially because of why. It's going to depend on the identity of H and G. So the exact relationship between these structures is really going to have to depend on what you've defined all of those substituents to be. If they're all identical, then they aren't enantiomers, they're identical. Right? If they're different, that's when things start to appear and we get complications within that. Kind of, sort of? So that's our core piece. And exactly what you got up, there's a summary side that has a giant red box, and what I'm trying to show within that red box is exactly this. Right? And you are absolutely welcome to try and memorize that. Right? Point value for the amount of questions, it really isn't worth the struggle to learn, if I'm going to be brutally honest. Okay? So we talk about it, you will have your brain melt trying to deal with it, particularly dealing with the smart work as you're trying to process all of those pieces, because it's a challenge. Okay? But when it comes to the exam, I'm not going to ask a whole bunch of questions on it, because it isn't that high value of a concept. Right? What it does do is it brings in everything. We've got p orbitals, we've got additions, we've got cyclic reactions, we've got chirality. Okay? We have cis and trans appearing up in it. Right? To add to the kind of insult to injury on this, what shape did we produce at the end? Cyclohexene officially, right? But what do we know about cyclohex structures? Don't remember anything about cyclohex structures? What's that? No, actually they do rotate. That hand gesture was the right gesture. They do chairs, which means, could you see the products drawn like this? Yeah. You could also see the chair version of this drawn out. and you would have to interpret the chairs. So Diels-Alder covers the whole frickin' gambit of everything that you could have possibly learned in OChem 1, right? And just throws it all at you at once. My recommendation is to do the best that you can with all that spatial awareness. It's going to be a struggle to go through with the homework. Talk to people. Build models to try and figure out how those things come together. Get through the homework faster. And then when it comes to the exam, don't frickin' touch it. Like, leave it alone, finish everything else, and then come back to it. Because the odds are that you're just going to get it wrong. And that's not saying you are low value. Odds are, am going to get it wrong too, right? So I don't want to spend my time on something that I'm likely to get wrong. Make sense? Okay. There are other things that can kind of change within this system. This is the core kind of fundamental piece. What happens if I do this? What changed? I added another pi bond. Is there still a pi bond that can react? Yeah. So what's the product going to end up being?
You have to add another pi bond from the product, because you only react one.
I only react one of the pi bonds, okay, on the dienophile. So I get a leftover pi bond on the other side. Okay? Most of these reactions are trying to get you to recognize the pattern of the core functionality. Once you recognize the pattern of your core functionality, how can you modify and tweak things afterwards to actually prove that you understand what happens when you make those changes? So when you're looking for a Diels-Alder, or you suspect that you have a Diels-Alder, what should you expect to see in your product? This is a horrible example, but whatever. Is there a pi bond in that product? Did you do a Diels-Alder? No. So there's one option. Look at your starting materials and look for a diene, a structure with two doubles bonds, and look for a second structure that has at least one pi bond. Okay? So you could look for that in the reactants. Okay? So if you see that in the reactants, you know you've got a Diels-Alder. What should you be looking for in the answer? Say it again. A cyclohexene. You need to be looking for that core piece. Anything that's missing on either end of that, okay, those are wrong answers. The rest is then saying, well, but this one has this thing in it and this thing in it. How does that change the chemistry? Okay, well now you've got to piece through how those things would connect. Okay, kind of makes sense? Other complications with the Diels-Alder, because according to my clock, I got a minute left. The dienophile, the single double bond, there isn't a whole lot we can do to this one to mess with it. So we'll leave that one alone for the moment. There is something we could do to mess with this. What is the difference between the diene and the dienophile? What is the difference between the diene, and the other one? The thing that reacts with it. You're looking at the substituents, and we need to recognize the core functionality first. Right idea, wrong direction. How are the two pi bonds connected to each other? Through how many sigma bonds? Just one sigma bond. And what is special about sigma bonds? They could rotate, which means I could draw the diene like this. Does that look like it's going to do a Diels-Alder reaction anymore?
Still can though.
It still can, because what could it do?
It rotates.
It can do the rotation to bring it into alignment so that it could react. Okay? So you could look at your starting material and be like, oh, that doesn't look like the C shape, so it doesn't work. Sigma bonds are allowed to rotate. Don't let that misguide you. Okay? On top of which, now I go back to those substituents. I now throw that in there. When you do that rotation, where does that extra bond appear? Is that now down here or up here? Okay, it is the up. How do you know that?
Because it's up on the other direction.
Okay, so we do got to be a little careful with that, because a structure like this would probably be turned sideways. Nope, still up.
Would it be at the top?
That double bond is clearly that one. So this is this one. This one has an extra substituent. How is the red one different from the blue one?
One's internal, the other's terminal.
Okay, and if something is an internal double bond, how does that make it distinctly different from an external double bond? What is now?
Substituents.
What does that more substituents potentially bring up as an issue? It's not resonance. What's the difference between the blue structure and the black structure?
It's structure.
Some trans.
Cis and trans. This is cis, which means when it comes out over here, it also has to be cis. You can't rotate that double bond. The only thing you could rotate was the sigma bond. Okay? So you have to pay attention to that as you move through, so that when you redraw it in the configuration that you want to do, you aren't also rotating the double bond. Okay? That's another common mistake. Okay? With that, I'm going to have to stop because we are done, but I will say that resonance does come into play. Okay, when we talk through how these Diels-Alder reactions can work. If I put a nitrogen, or actually I'm going to switch it up. If I'm going to put an atom X with lone pair electrons that can donate, those electrons can donate down, making this carbon particularly nucleophilic. Okay, so that carbon should be the one that starts my reaction. And because it is the negative, what should it connect to? A positive. So what I would have to do is go to the other side and see if I can find a difference between either of those carbons, deciding which one's more positive. So what could I do there? Well, we could add another functional group out here. Okay. Which carbon is more positive? The top one of my dienophile or the bottom one? The bottom one, because resonance, this connection has to align, where now atom X needs to be close to that carbonyl, not flipped the other direction. Okay? So resonance will also show up in this when you try and deal with some of these reactions. Okay? I believe the way the smart work functions first and foremost is it goes through simpler versions where we aren't dealing with resonance, okay? And you're dealing more with just the spatial arrangement of things, so you tend to get symmetry through your products and starting materials. And then it brings in asymmetry, and when we bring in asymmetry, that's where we're bringing in the concept of resonance. Okay, so if you're looking at your diene and your dienophile and you're like, that's not perfectly symmetric, you should be a little concerned that you need to be thinking about resonance as a potential option. Okay?